I was waiting at the bus stop the other day. This guy next to me starts talking to me. He goes like, "You know calculus, right?" I said, "Yeah, of course I know calculus." He said, "Okay, what's the limit as x approaches 2 of x squared?" I thought for a second and said 4. He said, "Well, prove it." I didn't know what to do. I just started looking around and, well, I just called my mom to come pick me up. I didn't know how to prove the limit. So these last 3 weeks, I've been working on exactly that. Trying to figure out how to prove the limit. And that's what I want to talk about today. When you're first introduced to the limit, you've got this loosey-goosey definition.
You can't be like all loosey-goosey having a sandwich, being on your phone.
As x approaches c, the function approaches some L. But in math, we need to be precise in order to prove things. So we use this formal definition here. That's called the Epsilon Delta definition. And we throw in some Greek letters to make it look fancy. And then we can formalize the definition of the limit in order to prove that they exist. Well, take a look at what it means. If the absolute value of x minus c is less than delta, so that means the distance between x and c is less than some delta, then the distance between f, the function at x, and L is less than some epsilon. So, in total, you can have any epsilon of your choosing. Then there exists for sure a delta such that the bound on x implies the bound on the function. Okay, we've got too many letters going on here, so we need to simplify this. And just remember this with this mnemonic. Okay, we go epsilon, for any epsilon, there exists a delta, such that the bound on delta implies the bound on epsilon, okay? Epsilon, delta, delta, epsilon. Every dog does. Excellent. No. What does this mean in practice? Well, you've got your function here. You've got your c value too. You've got your L value, L. Means for any bound on L, you can come up with a bound on x such that that bound implies the bound on the function. So what does the limit definition mean in practice? We can take any bound between the function and the limit, and that's epsilon. Then there must exist a bound on x between x and c, such that that bound implies the bound on the function. Now, how do we prove that limits exist then? Okay, let's say you plug in your limit, you get, limit as x approaches 2 of x squared, plug in, you get 4. That's fine. But to prove it exists then, we need to work with this definition, okay? We need to find a delta for any epsilon. So you're wondering, how do you apply this definition? You got all these epsilon, you got all these deltas, I don't know what to do. Well, the key thing to note here is that you can choose any epsilon and you can find a delta that satisfies this implication. So what that means for you is you want to find a delta in terms of epsilon. If you find delta in terms of epsilon, then any epsilon you choose is going to work out, guaranteed. So how do you do that? Well, it turns out that you want to work backwards. You want to start with the implication, what's implied. Epsilon. Assume this to be true. Work backwards, figure out what delta would be. Assume that delta then and then work forwards to solve for the implication. Like I said before, we want to figure out what delta is in order to prove this implication to be true. How do we figure out delta? Well, we start from the back. We start working backwards. All right, so we're going to assume this to be true now. What does that mean? Well, let's plug in f of x, let's plug in L, and we'll see. That means we got, so f of x is x squared, right? That's just the function itself. L is the limit that we're testing out. Epsilon is still epsilon. No getting around that. Okay, now we want to figure out what is delta. So, how do we figure out delta, you ask? Well, we know that delta is greater than absolute value of x minus c. What is x minus c? Well, c is 2. So, how do we rewrite this in order to get it into this form, involving delta and absolute value of x minus 2? Okay, you go back to 7th grade in your algebra class, and you do this. Okay, now you got x plus 2 times x minus 2 is less than delta. Alright, now you've got x minus 2 absolute value times absolute value of x plus 2 is less than epsilon. So, next step. What does this imply? Well, we know absolute value of x minus 2 is less than epsilon over absolute value of x plus 2, right? And now, there you go, boop bop bam, we've got it in the form we need. But wait, there's more, okay? We've got delta here in terms of x. We don't want delta in terms of x, because we got x in terms of x, delta in terms of x, it's not good. We need delta in terms of epsilon. We need x in terms of delta. We need delta in terms of x. But if we got x in terms of x, it doesn't work, okay? It breaks down. Everything's wrong. So, we do something sneaky here, okay? It's a little trick. It's a high-level trick. This is one trick I want to tell you. All right, here's the trick. So, we know delta is small. We know epsilon is small. What does that mean exactly? Well, small, maybe less than 1 or so, okay? So, if we say that delta is going to be less than 1, what does that mean for x? Well, x is approaching 2. Delta is less than 1. The distance, the delta, the x. Okay, so maybe we say that delta is less than 1. That implies that x is between 1 and 3. The distance between x and c now is less than 1. Alright. I think that is good. So, now that we've got that, what do we need to do next? Well, we want to write this equation, do some manipulations, get it in terms of what we have here with relation to absolute value of x minus 2. The idea is, if we can rewrite this into this form up here, then we can figure out how to relate absolute value of x minus 2 into delta without involving x on the right hand side. So we do this. We add 2 to each side, right? X plus 2 is less than 5. Take the absolute value now, and we get absolute value of x plus 2 is less than 5. And now we can take the reciprocal of each side. And remember, when you take the reciprocal, you want to flip the inequality. X plus 2 is actually now greater than 1 over 5. Multiply through by epsilon, and we've got epsilon over 5 is less than epsilon over x plus 2. And there we go. So we've got this now. We can relate it to this, and then we've got epsilon over 5. So concretely, we have absolute value of x minus 2 is less than epsilon over 5, which is less than epsilon over x plus 2 absolute value. We're going to let delta equal epsilon over 5. We did it backwards. We took the implication, we worked backwards, we solved for delta. Now we want to work forwards to actually prove it. We've got a good guess on what delta should be, And we're going to take that to prove the implication. So coming back to the implication here, we want to show that x minus 2 is less than delta implies that x squared minus 4 is less than epsilon. We're going to take the delta and we're going to take x minus 2 absolute value. We're going to plug it in like we had before. And then we're going to somehow get this. How do we get that? Well, algebra. We start off, we multiply each side by x plus 2 absolute value. We can simplify. So on the left hand side, we're going to get absolute value of x squared minus 4. And then we get epsilon over 5 times absolute value of x plus 2. Next thing we want to notice is going back to our definition here. When we assumed that x would be between 1 and 3, we saw that epsilon over 5 was guaranteed to be less than epsilon over absolute value of x plus 2. What this means is that then we can say this inequality is extended to be less than epsilon over absolute value of x plus 2, right? Substitute that in, and then times the absolute value of x plus 2 from over here. So now simplifying even further, on the left hand side we've got x squared minus 4 absolute value, which is now less than just epsilon because these two cancel out. And that is the implication that we wanted to solve for. So, to review, we want to prove this implication that the bound on delta implies the bound on epsilon. And that's exactly what we did. The first step we did was we took the assumption that the bound on the function is less than epsilon. We plugged that in and we worked backwards. We tried to solve for delta, but we just got x in terms of x. So the next step we did was made a simplifying assumption. We assumed delta to be less than 1, and then we figured out a suitable delta. We took that delta and then worked forwards. We solved for the implication and we found out that delta worked after all. So what we found in total is that for any epsilon greater than 0, there is a delta such that delta equals epsilon over 5, such that the bound on x implies the bound on the function, and therefore the limit as x approaches 2 of x squared equals 4. That is how you prove a limit.